Hello Flight Simmers and welcome back to Alpha Hotel Flight Simulator Training. This is flight lesson number 7 in our instrument training series. This video will be part 1 in a 3-part series taking an in-depth look at localizer approaches. In this video, we'll take a look at localizer approaches and how to fly them. In the videos that follow, we'll take a short IFR flight to demonstrate how to navigate onto and fly the approach. First with the G1000 equipped Cessna 172, then with a Cessna 172 Classic Analog or Steam Gauge panel. Before we begin this video, I'll mention that, like with other instrument approach lessons, it's a good idea to be familiar with certain topics related to instrument flying prior to watching this video. First, it's very important to be familiar with the basics of instrument flying, as well as having a fundamental grasp on how the basics of instrument approaches work and how to read instrument approach charts. It's also a good idea to be familiar with how an ILS works, since the two approaches use similar components, though I will be going over the components of that system that are used on a localizer approach in this video. It's also a good idea to be familiar with the basics of VOR and NDB navigation, as well as knowing how to use distance measuring equipment or DME. We'll be demonstrating the approach with both the G1000 equipped Cessna 172 that's available in the standard edition of the sim and the 172 Classic Analog or Steam Gauge panel that's in the deluxe edition. If you're going to fly the approach with the G1000 equipped 172, you'll want to be familiar with the G1000 and have a basic working knowledge of how to use both an HSI and a flight director. If you plan to fly the approach with the 172 Classic, it's a good idea to be familiar with the GNS 530 and 430 units that are installed in the aircraft. We won't be using the GPS functions of those units or the G1000 with this approach, but we will be using some of the non-GPS functions of each unit. I'll leave links to the videos on all of those topics, plus a link to the entire instrument training series in this video's description. So what is a localizer approach? A localizer approach is an approach that uses an ILS localizer transmitter to provide lateral guidance to the runway, but does not use a ground-based glide slope transmitter to provide vertical guidance like a full ILS system. So basically, it's an instrument landing system or ILS approach that does not have a glide slope for vertical guidance. It should be noted that most standard ILS approaches can be flown as localizer approaches. You'll notice that on the procedure title for an ILS approach, it usually says ILS or localizer approach, meaning the plate can be used to shoot either type of approach. For example, if we take a look at the approach plate for the approach that we use to demonstrate ILS approaches, the ILS to runway 36 at New Century Air Center in Olathe, Kansas, you can see the approach title or approach plate title does say ILS or localizer approach. And then if we look at the plan view, there are several elements on the plan view that are for the localizer approach only. The Maltese cross here and its associated DME is used to identify the final approach fix for the localizer approach. You don't necessarily need that to shoot the ILS. And then the step down fix and the visual descent point are also only for the localizer approach. You can see those are marked with asterisks there, and it says over on the side that this is only for the localizer approach only. You don't need to worry about those if you're shooting the ILS. And then the missed approach point, which is the end of the runway and has a DME distance from the localizer transmitter, is also something we typically only use on the localizer approach. It's not uncommon in the real world for an ILS glide slope to be inoperative, necessitating that an approach be flown as a localizer approach. In Flight Simulator, however, as far as I know, there's no way to render the glide slope inoperative on an ILS approach. So the only way to shoot a standalone localizer approach to a runway that has a full ILS system is just to ignore the glide slope or to use an aircraft that has a VOR radio with no glide slope receiver. Unfortunately, as far as I know, the only aircraft that fits that bill in Flight Simulator is the Robin DR400, and it's not well equipped or certified for instrument flight. There are, however, many localizer approaches that were designed as standalone localizer approaches. These approaches were designed and built without a glide slope, so they're probably the best way to learn to fly this approach type in Flight Simulator, and that's the type of approach we'll be discussing and using to demonstrate this procedure. A localizer approach has many of the same components that an ILS system has. For the ground-based components, it's going to have a localizer, which again gives you lateral guidance to the runway. It will typically have an approach lighting system of some kind, although it may not be the same type of approach lighting you're used to seeing on an ILS system, although it could be. It may also have marker beacons or compass locators, which are small, low-powered NDBs, although I have not been able to find any approach plates or approaches out there that are currently using these as far as localizer approaches go. Technically, the only onboard equipment you need to fly a localizer approach is a VOR receiver, and again, it doesn't have to be one that has a glide slope display, although pretty much every airplane in flight sim that you can fly IFR does have that. Realistically, you'll also need something to tell you how far from the runway you are, and what type of equipment you'll need for that will depend on how the approach is designed. By far, the most common type of equipment that's used is distance measuring equipment, or DME. Gives you very precise location information. That's what most of the approaches use. But there are some other ways to do it. You may need a second VOR receiver to use VOR cross radials to identify the fixes on the approach. The fixes may be identified by marker beacons, so you would need a marker beacon receiver, although again, I haven't seen any approaches currently that are using that. You could need an ADF receiver. Sometimes you may fly over a compass locator, that low-powered NDB, and that will tell you that you have crossed a fix. And there are some approaches out there, at least there used to be, that where you would identify your fix with an NDB bearing. Although again, those are fairly uncommon, and I have not seen any of those lately, so those might have all been decommissioned. So as far as the approach minimums go, localizer approaches will typically have ceiling minimums as low as 330 feet above the touchdown zone elevation, and visibility as low as 1/2 statute mile or RVR of 2400. These minimums are greatly dependent on what type of approach lighting system that runway has, if any. And it's also, just like an ILS approaches, will be tailored for the runway the approach serves and the local terrain, so those minimums may be higher. So let's do a quick review of how a localizer works. The localizer is a system that gives you lateral guidance to the runway. You can think of it as being like a VOR, but instead of putting out 360 radials, it puts out only one course, and it's pointed straight down the runway it serves. In addition to having only one course, it's also more precise than a VOR. Whereas a VOR will go full-scale deflection on the CDI needle when you're 10 degrees or more off course, a localizer needle will go full-scale deflection when you're only about 2.5 degrees off course, so it's roughly 4 times more sensitive or more accurate than a VOR. The width of a localizer course can actually be between 3 and 6 degrees side to side, depending on the length of the runway it serves. Like a VOR radio, the course gets narrower as you approach the transmitter, and it will be calibrated so that the course is 700 feet wide side to side, or 350 feet each side of the center of the course at the runway threshold. Localizers transmit on frequencies between 108 and 112 megahertz, which is the same as the lower end of the VOR frequency range. Because of this, frequencies with odd 10th decimal places like 108.1, 108.15, 108.3, and so on are reserved for localizer transmitters. Localizers also broadcast an ID signal like VORs that you can use to make sure you have the right station tuned in. All localizer identifiers will be 4 letters and start with the letter I. Like VORs, localizers can also be equipped with distance measuring equipment, or DME. We can tell if a localizer is so equipped if the nav data box for it has a channel frequency on FAA charts. The range of a localizer transmitter is 10 nautical miles if you're within 35 degrees of the course, and out to 18 nautical miles if you're within 10 degrees of the course. This distance may be greater if it is charted as such on the approach plate, but this is fairly rare for standalone localizer approaches. Localizer course indications work just like VOR course indications. The line or needle running vertically down the middle is your course deviation indicator, or CDI. The circle in the center represents your aircraft. If the needle goes off to the left, the course is to the left of your aircraft and the aircraft is to the right of course. You need to correct back to the left to get back on course. The opposite is true if the needle is off to the right. When you're receiving a localizer transmitter with a traditional VOR receiver and display, turning the OBS knob does not affect the course indication like it does with a VOR, since there's only one course being transmitted. Good operational practice is to select your inbound course as a reminder, but this will not affect the course indication. Most electronic HSIs will automatically set the localizer course for you. The G1000 in the game will do it automatically anytime you dial a localizer that's in range. Though with some EFIS systems in the real world, you do have to load the ILS approach in the GPS or FMS for it to set the course for you. If you're flying an aircraft with a mechanical HSI, which are only third-party aircraft right now, you want to rotate the OBS so that the arrow is on the inbound course. Again, this doesn't affect how the localizer indication functions, but it presents a pretty confusing picture if your course needle is way off from the course you're supposed to fly. To track the localizer with an autopilot, you typically just engage the same nav function you would use to track a VOR course, but some autopilots do have dedicated functions for tracking localizers. All right, so we're about 12 miles to the north of Fayetteville's Drake Field. We can see the approach lights out there on the horizon. And we'll go ahead and take a look at how a standalone localizer works. I have the frequency for the localizer to 16 at Drake Field in the standby. I'll go ahead and flip that over to the primary there, and you can see when I do that, the nav flag goes away and a course line shows up, but the glide slope flag still stays in place, telling me that I don't have a glide slope for this particular localizer. Other than that, it works like a normal localizer. You can see it's only got the one course, so I can twist the OBS as much as I want. That course is not going to move. Moving the OBS doesn't do anything to that. And then it indicates, as you can see, we're a little bit off to the left of the runway here. So it's showing the course is off to the right. We need to correct back to the right. So I'll put it into heading mode here, make a slight right correction to go and intercept that. And then once I get pretty well centered up, I'll arm the nav and it will go ahead and track the glide slope. So other than not having a glide slope, it works just the same as a localizer on a full ILS system. Even though the only component that's missing on a localizer approach compared to a full ILS is the glide slope, it makes the way we fly the approach significantly different than the way we fly an ILS approach. Since it lacks vertical guidance of any kind, the approach is considered a non-precision approach, or more precisely, an approach without vertical guidance. With this type of approach, rather than intercepting a glide slope or glide path to start our descent, we fly to a geographical point called the final approach fix, which is marked on the chart with a big black X called a Maltese cross. Again, this point can usually be identified with DME distance, a VOR cross radial, a marker beacon, or an NDB or NDB bearing, with DME being the most common way to identify it. Once we cross the final approach fix, we descend to a minimum descent altitude, or MDA, rather than a decision altitude. The MDA should get us low enough to see the runway and continue to a visual landing. If we don't get the runway in sight, we need to execute the missed approach when we arrive at the missed approach point, or MAP, which, like the final approach fix, is a geographical point. It can be identified with something like DME or a VOR cross radial, just like the final approach fix, and DME is the most common method. Though with some approaches, you can even use timing from your final approach fix to identify when you've arrived at the missed approach point, though this is a fairly rare technique to find nowadays. There are two different techniques you can use to descend on an approach that doesn't have vertical guidance, and I do a deep dive on how to use those two techniques in a separate quick look video that I'd encourage you to check out. I'll leave a link in this video's description. To fly our demonstration approach, we'll be using a technique called the Continuous Descent Final Approach, or CDFA. Here's a quick review of how that works. To fly a CDFA, we want to start our descent at the final approach fix, but we use a somewhat gradual, targeted descent rate to stay on the descent angle for the approach, rather than rapidly descending and leveling off at the MDA. We monitor our descent by cross-checking our altitude versus our distance from the runway and adjust our descent rate to stay on the descent angle for the approach. we descend down to a derived decision altitude, or DDA, which we treat just like a decision altitude on an approach with vertical guidance. When we arrive at the DDA, we either descend for a visual landing if we have the runway in sight, or we execute the missed approach procedure. There are 5 steps that you want to use when you are preparing to shoot a continuous descent final approach on an approach without vertical guidance. The first step is to determine the descent angle for the approach. This is called the visual descent angle, or VDA. Then you want to determine what the target descent rate should be for staying on that visual descent angle. Then you want to calculate your derived decision altitude. Then you want to calculate descent cross checkpoints so you can see if you're high or low as you're coming down. And then you want to adjust your descent rate as needed as you're flying the approach based on the altitude that you cross each cross checkpoint at. So determining your visual descent angle is fairly straightforward. All you need to do is look on the profile view of the chart. So we'll pull up the profile view for the approach we're going to use to demonstrate a localizer approach, which is the localizer to runway 6 into Drake Field in Fayetteville, Arkansas. The ICAO identifier for that field is Kilo Fox Yankee Victor. And we just look on the profile view. We look for this little angle symbol here, the little degree symbol here, and that number beside it tells us what our visual descent angle is. So on this particular approach, it is a standard 3-degree visual descent angle. So that's the angle that we will be coming down from the final approach fix to the touchdown zone at. Underneath it lists our threshold crossing height. This will be important for calculating our descent cross checkpoints. And this just tells us that if we start our descent at the final approach fix and we use this 3-degree visual descent angle, if we stay on that angle, then we will cross the threshold at 50 feet. As we're coming across the runway threshold, we will be 50 feet above the touchdown zone elevation. So our next step is to determine the descent rate that we need to stay on that visual descent angle. And this is pretty much the exact same process that we use to determine our target descent rate to stay on a glide slope for an ILS. So we need to pull up the FAA's climb and descent table. And again, you can find this by doing an internet search for FAA climb and descent table. And again, many flight planning apps and chart apps have this somewhere in their app as well. So the first thing we want to do is go over here to this column that says vertical path angle, and we find our visual descent angle in there. So we had a 3-degree visual descent angle. So this is the row that we want to use right here. Next to that, we have feet per nautical mile. We'll use that for calculating our descent cross checkpoints, but we'll ignore it for right now. And then over here, we have our ground speed. So this tells you in these columns here what ground speed you're going to, or what descent rate in feet per minute you're going to need to fly a given visual descent angle based on your ground speed. You'll notice we have 60 knots and 90 knots. Unfortunately, we are flying the approach at 70 knots of ground speed, roughly. So we'll need to average these two numbers, and that will give us the descent rate for 75 knots, but that will get us close enough. You don't have to be super precise on this. So we can see the descent rate at a 3-degree angle at 60 knots is going to be 318 feet per minute. At 90 knots, it's going to be 478 feet per minute. So we average those two together. So our target descent rate is going to be 398 feet per minute for a 75 knot ground speed, or about 400 feet per minute is what's going to keep us on that vertical descent angle. You can also do a quick calculation to determine this descent rate, and it's not as precise as using the chart, but again, you don't need to be super precise. What you want to do this is for a 3-degree glide slope or 3-degree visual descent angle, and this only works for 3 degrees, is you want to multiply your ground speed by 5, or you can divide by 2 and multiply by 10. Divide your ground speed by 2 and multiply by 10. It's just two different mathematical ways to get to the same answer, whatever works best for you. So for an example, at a 70 knot ground speed, if we multiply that by 5, or divide by 2 and multiply by 10, that gives us a 350 foot per minute target descent rate. So you can see pretty close to what we calculated for the 75 knot ground speed using the chart. And again, it's close enough to get you in the ballpark and adjust from there. Most of the time, if you're using an autopilot, you can only adjust the descent rate in hundreds of feet per minute anyway. So it's going to get you close enough to get you, close enough to the target descent rate to keep you on the path. So our next step is to calculate our derived decision altitude, and this is, again, the altitude we're going to use instead of the MDA, and we're going to treat it like a decision altitude. In other words, we're going to descend down to that altitude, and at that altitude, if we do not have the runway environment in sight, or at least the approach lights in sight, we're going to go ahead and execute the missed approach procedure. All you need to do to calculate a derived decision altitude is add 50 feet to your MDA for the approach. So for an example, looking at our localizer approach to runway 16 in Fayetteville, Drake Field at Fayetteville, Arkansas, our MDA for category A and B aircraft is going to be 1,780 feet. So we add 50 feet to 1,780 and we come up with 1,830 feet for our DDA. So the next thing we want to do is calculate our descent cross checkpoints, and what we do is calculate these once every mile, and this tells us whether we are high or low as we're coming down on the approach. So the descent cross checkpoints, we want to calculate what altitude the aircraft should be above the threshold crossing height for each mile we are away from the runway, starting at the threshold and moving back to the final approach fix. So to do this, we want to first find our vertical path angle, which again is 3 degrees on the localizer to runway 16 in Fayetteville. It tells us that for every mile we move away from the runway, we should be 318 feet higher. So for example, at the runway threshold, we should be at the threshold crossing height. At 1 mile away from the runway, we should be 318 feet above the threshold crossing height. We add another 318 feet to that at 2 miles, which gives us 636 feet. And we add another 318 feet for that at 3 miles, to that at 3 miles, and that gives us 954 feet above the threshold crossing height. We don't have to calculate any further because the final approach fix is less than 4 miles from the runway threshold, so we can go ahead and stop there. Of course, this tells us how high above the threshold crossing height we're going to be. It doesn't tell us what our altimeter should show, and that's what we need to know. So how do we calculate that? So the first thing that we need to do is figure out what our altimeter should read as we're crossing the threshold. And again, on the profile view, it shows us that the threshold crossing height for this approach is 50 feet. And so that means that we should be 50 feet above the touchdown zone elevation as we're crossing the runway threshold. And the runway touchdown zone elevation is 1,252 feet. So if we add those two together, our altimeter should say 1,302 feet, roughly, as we cross the runway threshold. Now we just need to add 318 feet to that threshold crossing altitude as we move back away from the runway. So at 1 mile, we're adding 318 feet to that. That gives us 1,620. So at 1 mile away from the runway, we should be at 1,620 feet on our altimeter. At 2 miles, we add another 318 feet to that. That gives us 1,938 feet on our altimeter. And then at 3 miles, it's a total of 954 feet. So that should be 2,256 on our altimeter. And again, there's no reason to calculate it out to 4 miles because the final approach fix is not quite 4 miles from the runway threshold. So that tells us how far away we are from the runway when we should be at those altitudes. But the problem is we don't have any way to read our distance from the runway threshold. All we have is DME readouts, and the runway threshold is located at 1.2 DME, not 0. And that's because the DME transmitter and the localizer transmitter is at the opposite end of this 6,000-foot runway. So when we cross the runway threshold, we're going to be at 1.2 DME away from that transmitter. This is a pretty simple fix. All we need to do is add 1.2 DME to each of these distances, and that will tell us what our DME readout should be at each of these points. So when we reach 2.2 DME, we are 1 mile away from the runway threshold. We should be at 1,620 feet. When we're at 3.2 DME, we're actually 2 miles away from the runway threshold, so we should be at 1938. 4.2, we're at 3 nautical miles away from the runway threshold, so we should be at 2256. And again, we don't need a 5.2 because the final approach fix is located at 5 DME, so it's not quite 4 miles away from the runway threshold. So the last thing that we want to do is, as we're flying the approach, is cross-check our altitude against the altitudes that we have listed here at the points we have listed here. What I like to do is write them down on something that I can reference while I'm flying the approach, and I write them down in the order that I'm going to encounter them. So 4.2 DME will be first. That's the 3-mile fix, the 2-mile fix, and the 1-mile fix. And then I also write down my DDA since that's not anywhere on the chart. So I will fly to my final approach fix, which is hog intersection, identified with 5 DME from the localizer. And I will start my targeted descent at that point at about 400 feet per minute in the 172. And then when I get to 4.2 DME, then I'll take a look at my altimeter, and I should be around 2256. If I'm up around 2350, then I know I'm a little high and I need to increase that rate of descent. If I'm down around 2100 feet, I'm a little low and I need to decrease my rate of descent. So I'll make that adjustment, and then I'll check again at 3.2 DME. And again, do the same thing. If I'm high, I will increase the rate of descent. If I'm low, I will decrease the rate of descent. And then I will do that until I get to my DDA, and then I will treat the DDA just like a decision altitude. I'll look up. If I see something, I'll go ahead and descend to a visual landing. And if I don't see anything, then I can go ahead and execute that missed approach. One last thing I want to mention is that we have this big black V symbol on here. This is a visual descent point, or VDP. This tells you two things. First of all, it tells you that this is about the point that you will reach your DDA on the approach, because if you reach it and have the airport in sight, you can go ahead and just continue the descent to a normal visual landing. It will keep you on a nice vertical path to the runway from there. The other thing it tells you is it is actually legal if you wanted to level at the DDA. If you did not have the runway in sight, it is legal to do that and continue to fly to the missed approach point. The problem with this is the further you get past this visual descent point, the more likely it is that you're going to be too high to be able to execute a normal descent to the runway, even if you get the runway in sight at that point. So you need to be aware the VDP on this approach is 2.7 nautical miles. You're moving towards the transmitter, so the numbers are going to get smaller. So the further you move past 2.7 and the closer you get to 1.2, the less likely it is that even if you see the runway, you'll be able to execute a safe descent to the runway from the point you're likely going to be too high. And even if you see the runway, you're probably going to have to go missed approach. So that concludes part 1 of this video series on localizer approaches. Make sure to watch for the next 2 videos in the series where we get in the airplane for a short IFR flight to fly the localizer approach. As always, if you've enjoyed the content, please don't forget to like, subscribe, share, and ring the notification bell. Thanks for watching, and we'll see you next time.